Hello, my name is Dubiński and I would like to talk to you about our work, CDI, Copyrighted Data Identification in Diffusion Models. Contemporary diffusion models have amazed the world with their image generation capabilities. Key in enabling this impressive performance is the training of those models on large, diverse datasets. Those datasets are often sourced from the internet, and sometimes even without regard to the intellectual property rights of data original owners, such as artists or media providers. This has sparked numerous controversies which resulted in legal cases. As those cases are still ongoing and massive datasets continuing to play a key role in training of state-of-the-art machine learning models, the problem is bound to remain relevant in the future. In this context, it would be valuable to provide artists and media owners with a tool that would allow them to verify if their data was indeed used to train a particular diffusion model. Membership inference attacks seemingly present themselves as a solution to this problem. In general, membership inference attacks work in the following way. Given a sample S, the method queries the model M with this sample, and by analyzing the model behavior, such as the model's loss on this particular sample, arrives at a decision. Was the sample S used in the training set of the model M? However, we empirically find that modern membership inference attacks are limited in identifying training data of large diffusion models, such as those trained on ImageNet, achieving performance only slightly better than random guessing. A natural question arises: how can we do better? With the failure of membership inference attacks that try to assess the membership on the level of individual sample, we shift our focus to dataset inference, which aims to answer the question: was a particular collection of data points used in training of a diffusion model? Building on this, we propose our CDI method. First, we prepare two sets of images, P published and U unpublished. P published images are images that we suspect may have been used for training of a diffusion model. In contrast, U are images that we know were not used in training the model. In practice, those images may come from pictures released after the model was already trained and public, or images that were never published. The second step is extracting membership features from all samples in P and U. To this end, we use existing membership inference attacks as sources of membership features, and additionally propose our own feature extraction methods that strengthen the membership signal. First, we propose multiple loss, which measures the denoising loss of a sample at multiple time steps of the diffusion process. The intuition here is that the loss for membership samples that were used in training should be lower than for those that were not used in training. Secondly, we introduce noise optimization. In this method, we add random perturbations to a sample. We optimize this perturbation to minimize the model loss on the sample. The intuition is that this process is easier to perform on member samples. Finally, we introduce gradient masking. In this method, we mask part of the gradient for a sample at a particular denoising time step. The noise prediction loss under such gradient masking should be lower for member samples than for non-member samples. In general, the feature extraction step maps a collection of samples into a collection of membership features, which contain information about the membership of a given sample. In the first step of CDI, we divide features extracted from P and U into control and test sets. We train a scoring model S on the control sets on a binary task of predicting the membership of a sample. Then we assign scores to the test sets using this model. Higher score indicate that a particular sample is more likely to be a member of a diffusion model's training set. Finally, we perform a two-sample single Tate-Welch t-test. The null hypothesis of this test is that the scores extracted from P are not higher than the scores extracted from U. The outcome of this test is a p-value. If this p-value is below a significance threshold, we can reject the null hypothesis, which means that, in this case, P has been used to train the diffusion model. End-to-end, our CDI works in the following way. We prepare two sets of samples, P published and U unpublished. We map those samples into features containing information about the membership of a sample using our feature extraction methods. Then we train a scoring model on a binary task of predicting membership of a sample and use this model to assign membership scores to all samples in P and U. Finally, we compare the distributions of those scores using a statistical test. If the outcome of a test is a p-value below a significance threshold, we mark P as being used in the training set of a particular diffusion model. We investigate the effectiveness of CDI on modern diffusion models trained on different image resolutions and under different types of conditioning. We find that CDI is able to detect if a data collection was used in training of any of those models without data points. In some cases, we need as few as 100 samples. We also find that our new features greatly lower the number of samples needed to identify training data. In some cases, the drop is in order of magnitude. Moreover, CDI does not yield false positive. If suspect set P consists of non-members, samples not used in training of a diffusion model, CDI does not mark it as used with training of a diffusion model. Moreover, CDI also works if only part of the suspected data was used in training. Below, we see that CDI is also affected when the suspect set P contains non-member samples that were not used in training of a model. Let me now summarize our key findings. We empirically find that state-of-the-art membership inference method fail on large diffusion models. In this slide, we shift to a different paradigm, focusing on dataset inference to provide a tool for protecting the intellectual property in data collections. CDI is able to successfully and with statistical confidence identify data collections used in training of large diffusion models. Thank you for listening to this presentation, and I encourage you to reach out for the paper for more details about the method and more experiments.